Okay, PreCalc, the last section of Chapter 3, 3.5, Exponential Growth and Decay, and our favorite word, modeling data. So you're right, it's story problems, finishing up our chapter. As much as we hate story problems, it really does bring home, though, why we learn different concepts so that we can see where they might be used in real life, okay? And I will tell you on some of these models, some of these things, you may never see them, but one of your classmates may someday get into this field where they may see them. So we teach it to all of you so that you can see the application of it, and maybe someday you'll use it, maybe someday you won't, but it's good to have that in your repertoire of things that you are able to do and might be able to use someday. Okay, so we're going to start with exponential growth and decay models, okay? When you have something that grows, continues to grow, population is often used this way. The spread of the coronavirus is used this way right now. It's growing exponentially, right, is how they describe it. So it's increasing. So that looks like our first graph here. And by the way, that means that your base is larger than 0, okay? And I shouldn't say your base. It means that your power, right, or your constant up there is going to make things grow. And if your constant is less than 0, you're going to decrease, you're going to decay. Think about half-lives of things. Hopefully someday we'll say the coronavirus will be decaying because that will change over time because of a vaccination maybe. Okay, so here's what you have here. If your K, again, is larger than 0, you're going to see that increase. If your K is smaller than 0, you're going to see that decay or that decrease, okay? Let me move my page. Okay, so our first example, 1 here. In 1990, the population of Africa was 643 million, and by 2006, it had grown to 906 million. Use your exponential growth model, which, by the way, the growth models will be given to you when you need them. A equals A sub 0, e to the kt power, in which t is the number of years after 1990, to find the exponential growth function that models the data. Okay, anything with the 0 down there in the subscript, that's our initial. Okay, so we're talking about our initial population. The A without that is talking about the new one, okay? So first, let's figure out from 1990. We are now in 2006. So how many years have passed since then? If you want to do all this, right, we come over and borrow, then it becomes that, then we borrow again, and it becomes that, and we get, the 6 didn't need to borrow. What was I talking about? That stays at 10. 10 minus 9 is 1. All right, 16. Yeah, the hardest thing here is subtracting a 4-digit number from a 4-digit number, and I'm struggling with that. We could have a good set of notes here, right? Okay, that is my time. Since 1990 is 16. So in our growth model, okay, this is, again, I will give it to you. You don't have to come up with it yourself. I've grown to 906 million. My initial was 643 million. E is a constant. I don't know my that constant K. That's what I'm looking for, right? And I'm looking to see if it's plus or positive or negative. And then my time is 16. Okay. We learned what we did earlier this chapter, so we could solve for a variable that's in an exponential position. So keep in mind what we did in last section. We need to work first to get that exponential term by itself. So I'm going to divide by 643. And technically, I'm not going to divide. I'm just going to put it down there on the bottom. I'm going to write this 16K, okay? All right. Now that I have my exponential term by itself, how do I get the exponent out? This is where I'm going to take the natural log of both sides, okay? Now, it's super important when you take the natural log to say what was the number before you took it. So all of this is being taken to the natural, or has the natural log belonging to it, okay? The natural log and e over here cancels, so I end up with natural log of 906 divided by 643 equals 16K. Okay, so very important to realize that natural log was one natural log to that fraction. Don't make a natural log of 906 over a natural log of 643. Can't even read my writing anymore. That it's a division problem first, then you take the natural log. That natural log is an operation that if you do it too much, because like you distribute it, which you can't do, If you don't do it enough, okay, there's a difference in your answer. So it's so important to know the natural log goes to that entire chunk. So we're going to divide before we take the natural log. And then I want k by itself, so I'm going to divide by 16 after all of that. Notice that 16 is not with the natural log. It is completely separate. It's a whole number, a constant, okay? So in my calculator, I'm plugging in natural log 906 divided by 643, closing that parenthesis, dividing, and probably turning all that into a decimal and dividing by 16, okay? So important that you can do this on your calculator. So please, please have a calculator handy and run these through your calculator, because if you can't get the same thing that I get, we have an issue. And it might be me, but we need to know that. Okay. 906 divided by 643, all of that before you close the parenthesis, and then divide by 16. And I get this k value of 0.0214, okay? It's positive, which means my population is increasing, which by the numbers, yes, it was, right? So my model, when it says give me a growth function that models it, my growth function would be my population will become something from 643, which is where we started originally, e to the 0.0, I'm going to run out of space here, 214 t power, okay? That's my model. So the first thing I'm doing is just getting the model that I can use from here on out. So I used a data point to get that k number. It's positive because we're growing, and I get my model. Now for B, it says, in which year will Africa's population reach to 2,000 million, or 2 billion, right? That's kind of how I would read that. Okay. So same idea, but this time I'm going to reach 2,000, right? And that's why we're leaving it in millions, because the 643 was in millions, so we want this number to be in millions. That way I don't have to put all those zeros on either one of them. So I get 2,000 equals 643 e to the 0.0214 t. This time I'm solving for t for what year? Okay. Once again, it's in the exponent, but the rule is get your term with the exponent by itself first. So I'm going to divide by 643 on both sides next. All right, I'm going to leave it because I want everything as exact as possible. So I'm going to have e to the 0.0214 t and equals 2,000 divided by 643. Now that I have that exponential term by itself, I'm going to take the natural log of both sides. What I do to one side, I do to the other. These two cancel, and I'm left with 0.0214 t. On this side, it's the natural log of that entire chunk, right? I'm not going to break that apart. I'm not going to have two natural logs. I have one natural log to that entire number. I want t by itself, so I'm going to divide by 0.0214. T is going to equal that beautiful number, okay? So if somebody asked me what's the exact answer, I would say something, and it can't be exact because I rounded that 0.214 earlier, but we're going to type in our calculator, natural log, parenthesis, 2,000 divided by 643, close your parenthesis, get a decimal, divided by 0.0214. And this is going to give us approximately how many years? Okay. Natural log 2,000 divided by 643. Divide by 0.0214, and I get about 53.02. Okay, it says how many years. I'm going to say just 53 years, right? It says by which year? So remember, that was since 1990. So if I take 1990 and I add my 53 years, I get about 2,043. So we have about 23 years to wait to see if these numbers are anywhere close, right? All right. Using those logs, the exponential rules to solve for a growth equation, okay? Let's move on to page 2. All right. Strontium-90 is a waste product from nuclear reactors, and as a consequence of fallout from atmospheric nuclear tests, we have a measurable amount of strontium-90 in our bones, okay? So A, the half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of substance will have decayed to half the original amount. Find the exponential decay model for strontium-90. So we're going for the model first, okay? We're using that same equation we used on the other page, okay? That equation of A equals A sub 0 e to the kt power. And again, if needed on a test or quiz, I'll give it to you. Okay, this time, and they gave it to us, but it's not obvious. You have to stop and think. Okay, what was my initial amount and what is my new amount right now? Okay, so the half-life is what we're talking about. So half-life means after one half-life, you have half the amount left, okay? Here's the deal. You make up your own numbers, basically, for this. So how many do you want to start with? Hint, hint, make it even, okay? So let's say we started with 100, right, of strontium-90. So half-life would mean we'll be left down to 50 afterwards. Does that make sense? So you make up your own numbers, okay? I'm going to be honest, that's big. We could have done like 2 and 1, right? E, we're solving for K, and it says in 28 years is a half-life, okay? So that's what we're putting in, and we're solving for our K the first time. Keep in mind, should this be positive or negative when we get done? If we're decaying, it should get negative. Okay. Once again, I've got to get my exponential term by itself, so I'm going to divide by that 50, or by that 100. So I get 50 divided by 100 equals e k to the 28. Okay. Reduce that maybe to 1/2. There, it makes sense, right? The half-life now equals e to the 28. All right, solving for k, so let's take the natural log of both sides. So I have the natural log of 1/2 equals, those cancel, 28k. Solving for k, I'm going to divide both sides by 28. All right, that's what I'm plugging in my calculator, right? Natural log of 1/2 divided by 28. Parentheses are important there. I'm on track. I got a negative, right? I got negative, oh my goodness. I got negative 0.0248 when I round it, okay? So always 4 decimal places because we want that exact as much as possible. We could go more, but 4 is going to give us close enough. And then it gives us that model A equals A sub 0 e to the negative 0.0248 to the t power. Okay, that's my model. Okay, now it says suppose a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for that strontium-90 to decay to a level of 10 grams? Okay, so my initial amount here is 60. I'm decaying to 10 grams. It's e to the negative 0.0248 to the t power. Once again, t now is my exponent, and I want to get it by itself, okay? So I'm going to take and get my exponential term by itself first, so divide by 60. Get 10 over 60 equals e to the negative 0.0248t. You can reduce that to 1 over 6 if you want. Take the natural log of both sides. So I get the natural log of 1/6 equals negative 0.0248t because the natural log and e cancel. Divide everything by that nice pretty decimal. So t is going to be the natural log of 1/6 divided by negative 0.0248. All right, let's check to see what our time is here. I'm getting about 72.25 years. Let's just, like, it's like 72 in 4 months, right? A quarter would be about, okay, never mind. A quarter would be 3 months. Okay, let me not ad-lib anymore. Maybe I should stick to the script, right? Let's say 72 years. All right, new model. Okay, so we used that first model a couple times. This is a new model. This is a mathematical model for limited logistic growth, okay? And again, there's a job out there that uses this. Maybe out of the, 27 of you, one of you might go into that. But the other 26 of you just need to learn that, hey, this is something you should know about, okay? So let's go with it. All right, so we have this model where A equals C over 1 plus A times E to the negative BT power. A, B, and C are constants. C and B have to be larger than 0, okay? Really, that's all you need to know right now. Okay, let's put it into a perspective here of what we're doing. So I have a learning theory project. The psychologist discovered that this model, with all the numbers plugged in, is a model for describing the proportion of correct responses after T learning trials, okay? So it's saying, what's the chance you're going to get correct responses depending on how many times you've been taught this material, okay? So it says, find the proportion of correct responses prior to learning trials taking place. So that means I have 0 learning trials, right? So my T right now is going to be 0 on this first one, okay? Way to change the color. All right, so here we go. I'm plugging in f of 0, right? I get 0.8 divided by 1 plus e to the negative 0.2 times 0. All right, so I get 0.8 on top, on the bottom. Negative 0.2 times 0 is 0. So if I say I have e to the 0 power, well, what's anything to the 0 power? It's 1, right? So I get 0.8 divided by 2. It looks like I have a 0.4, or think about that as a 40% chance of getting correct responses with never learning about the material, I guess, okay? So it's not very high, 40%, right? So let's go and do the next one, which says, what if you've learned about it 10 times? Okay, so I have f of 10. I'm getting 0.8 over over 1. See, I can't even read my own writing. 1 plus e to the negative 0.2 times 10. Okay, gives me 0.8 on top. Okay, I need to take negative 0.2 first times 10, right? So I get like negative 2. I need to take e to the negative second power. And add it to 1. And that's on the bottom, right? And it's like, just so you know, it's like 1.1353, okay? And now I'm going to divide 0.8 by that, right? So 0.8 divided by. And I divide and I get about 0.704. About 0.7, right? So I've increased, I'm up to a 70% now. So it's not bad after learning about it 10 times, right? All right, the last question down here in the bottom is kind of learning what was going here. It says, what is the limiting size of f of t, the proportion of correct responses as continued learning trials takes place? Okay, so it's saying, I definitely increased, right, up to 0.7. So let's say I learned 100 times. I was taught at 100 learning trials, right, 100 or 1,000. What's the highest number I'm going to get out of here, okay? The limiting size. And some of it is just plain understanding our equation. I have this number of 0.8 here. And no matter what I do, I'm always going to have 1 plus e to a negative power, okay? That 1, e to the negative power is going to get smaller and smaller and smaller and smaller. So I'm always going to add 1 plus some smaller number, okay? So what's my limiting one? The c, okay? C is the limiting. Because what's going to happen is this little number underneath here is going to get closer and closer and closer to 0, but we know that e is never going to equal 0 exactly. So the best you're going to do is like 1.000000 and then some numbers at the end, right? And 0.8 divided by that 1 is going to be closest to 0.8. So what we get is 0.8. That's the best we can do with this model, okay? It's not saying somebody can't get correct responses, but it's saying that there is a limiting time, that you're not going to get everything possibly, okay? A model, that's what this is. Not guaranteed, but it's a model. All right, let's do another one. Where else do we use these, okay? This is Newton's law of cooling. And we get this equation, temperature equals C, which is your constant temperature, plus your initial temperature minus your constant temperature, times e to the kt power, and T is time, okay? One thing I do want to stress here is currently in these problems, our T is going to be in minutes, not in hours, not in days, not in years, okay? As long as we consistently use the same unit of time, we're going to be okay with this equation, okay? But you can't just use T for minutes one time and for days the next time. Just make sure we use a consistent little t, okay? All right, so let's try this. I have, and just so we know, the K, if the K, it's the law of cooling, so it should be a negative constant associated with cooling that, okay? So we have an object that's heated to 100 degrees Celsius. It's left to cool in a room that has a temperature of 30 degrees Celsius. And after 5 minutes, the temperature of the object is down to 80 degrees Celsius. Okay, so first we're going to find the model by finding what our K is. Okay, some things to think of. Your object was heated up, and now it's cooling. Heated and cooling. So your heated is going to be where you start at, your T sub 0. What it cools to is just your T. And the room stays a constant temperature, the heat or the air conditioning or whatever is on, right? That's your constant temperature, so that's your C, okay? And obviously we're going to deal in minutes here, so the little t is 5 minutes. Okay, let's plug and chug and see what we can figure out. So we cool down to 80 degrees. Our constant in the room is 30, plus our initial temperature was 100, minus our constant, which is 30, times e to the k to the 5 minutes there, okay? So in all this stuff, k is the missing part. That's what we're solving for. Okay, so let's do some math that we can do. I'm going to subtract 30 and make this 50. I'm going to do 100 minus 30. That's going to give me 70. E, and I'm just going to make it to 5k. Okay, remember, we get our exponential term by itself. So we divide by 70, and are you okay simplifying to 5 over 7 right away? Equals e to the 5k. Remember, so that's 50 divided by 70. I reduced them both by 10, and that's where I'm at. Now that I have my term all by itself, I can take the natural log of both sides. So I get the natural log of 5 over 7 equals 5k. So k is going to be the natural log of 5 over 7 divided by 5. All right, run that through your calculator. Remember to close your parenthesis after the 7, right? So the natural log of 5 divided by 7 divided by 5. I get a negative, which is good. That's what we were supposed to get, negative 0.067. I'm going to round to 3. Okay, so my model is my equation with that k in it. So t equals c plus t sub 0 minus c e to the negative 0.0673 to the t power. Okay, now we can use that model to continue problems with information that fits this Newton's law of cooling. So B says, what is the temperature of the object after 20 minutes? Okay. So let me go ahead and figure out the temperature after 20 minutes. So we don't know the new temp. We're still at a constant of 30. We still started at 100 minus 30, and we have this e to the negative 0.0673 times 20 minutes. Okay. This is straight up just calculator. That's really all we're doing right here, right? So, I mean, you could simplify it and you could say 30 plus 70 times e to the, I don't know, multiply that by 20, like negative 1.34, I don't know, 5.9, something like that. Okay. Calculator is so important here. Do it correctly or make sure you have the right pluses and minuses in the right spot. E, I would definitely use, well, the caret button shows up when you press E usually. Make sure that negative is on there. You cannot forget that. It is so important to have that on there to get that decay in there, okay? Or in this case, it's not really decay, it's the loss of temperature, right? And it looks like we have a temp of about 48.2 degrees. Okay. All right. Same model, different information here. When will the temperature of the object be 35? Okay, so I have 35 as my new temp. My room was at 30. I had 100 minus my 30. I have e to the negative 0.0673, and this time I'm solving for t, which is my time in minutes. Subtract my 30. 70 e to the negative 0.0, don't forget that extra 0.673t. Divide by 70. This one definitely makes a difference, right? Because it's 5 divided by 70 now. So I'm going to get 5 divided by 70 equals e to the negative 0.0673t. Take the natural log of both sides. The natural log of that chunk of 5 divided by 70 equals negative 0.0673t. And let's go ahead and divide by negative 0.0673. And it looks like my t is about natural log of 5 divided by 70. Close those parentheses. Divided by negative 0.0673. Ugh. I got an error on mine, so something didn't go right. All right, natural log of 5 divided by 70 divided by. Make sure your negative. I put a parenthesis now around what I have. I think that's what it was struggling with. Okay, I'm getting about 39.2. So it looks like at about 39.2 minutes, it'll take to cool down. Okay. Would anybody use this in a job? I would say definitely when you're working with machines, when you're, I don't know, you're working with steel or iron or aluminum, that you're like made a product and you need to cool it and you're trying to see like how long will it take for this to be cool enough that we can do the next process or we can pass it on or whatever. This is a big idea. I'm sure foundries, especially if there are such a thing, hardly anymore, use this, or any type of factory that's building things and, you know, using high temperatures to start with may need to use this law of cooling, okay? So just kind of an idea, and I'm sure it's all programmed into a computer, but you got to know behind the programs what's going on. That's what engineers often do, is it's reprogramming something, and so they have to understand this math behind it to get to where it needs to go. Okay, modeling data. So when data is presented sometimes, we don't always know, is it a exponential? Is it a logarithmic? What's it doing? So what you see here are 4 graphs just modeling what does that curve look like, okay? And you'll notice it's not a line because they are representing data points, basically. So it's saying if your data points are slowly started off really low, close to 0, and then all of a sudden they're growing very quickly up to the right, you're exponential, right? And your base is bigger than 1. If you had a lot and then all of a sudden it's going down, it's getting closer and closer to 0, that's exponential decay, right? And it's still exponential though, okay? And then you have these ones for the logarithmic where you can't even start in a negative world, right? You have to be in the positive, and we're growing up to the right, and remember the second one is actually that flipped, that have to think of the vertical reflection, right? So that's kind of where we're looking at some of these, okay? It's a trend, basically, is what you're looking for. Which way do your trends go? Okay, so let's look at this example. 5, it says the given table shows the population of various cities in thousands, and then the average walking speed in feet per second of a person living in that city. Create a scatter plot for the data, and based on the scatter plot, what function would be a good choice for modeling the data? Now, number one, we are not writing a function. We're simply saying, is it represented as an exponential or as a logarithmic? That's all we're trying to say, okay? So don't freak out here. And yes, apparently there's a difference in how many people live in the city and how fast you walk, I guess, is what this study is claiming anyways. Okay. My walking speed goes from like 0 to 0.5 to 2.5-ish, something like that, right? So I'll make that my short one. First, so 0, 1, 2, right? You know, up to 3, we're not really up there. Okay. My population is going in thousands, and we're as small as 5.5 thousand and as large as 342,000. Okay. So let's say this is 300,000, 200,000, 100,000. All right, so here's my population, right? Always good when you're drawing a graph to kind of scale it out first before you start putting any points here. And here's my walking speed over here. Sometimes it makes me wonder who comes up with what they're going to make for their study. Study what the walking speed is. Okay. All right, so in a population of 5.5 thousand, the walking speed is about 0.6. So I'm talking about, I mean, I'm right over here on this, I don't even know, on this axis right here, right? Maybe I need to be slightly up, right? So like right here, maybe. All right, and at 14, I'm at 1. Well, 14 is still pretty small on the grand scheme of things. At 71, I'm at 1.6, so about maybe right there. At 138, I'm at about 1.9. And at 342, I'm at about 2.2. Okay. Now, I don't really want to draw a curve, right? I want to just say, what are these data points doing? Because I don't connect them with a curve because it's not like there's continuous points in between them. This is just it. These are my data points. What trend does it follow, an exponential or a logarithmic? It looks to me like it's kind of logarithmic, right? So if this study were to write a model, they would need to use the logarithmic growth model, right? That's kind of what this is saying. All right, let's move on. Let's try another one. Similar idea, but with different data. This table shows the percentage of households in the United States with an HD TV sets for 4 selected years from 2001 through 2009. Create a scatter plot, and based on the scatter plot, what function would you may be a good choice for modeling the data? Okay. So obviously, our information or our data is a little bit older than where we're at right now, right? So years since 2000, well, between 2000 and 2009, and then what percent own a HD TV set, right? I would assume you get to a point where you're about the same. Okay, I need to give myself room to write numbers. Don't always plan this as well as I should. Okay, so let's just start in the year 2000, right? Go up to 2010. So 8, 6, 4, 2. I think that's what I'm doing here. Trying to kind of space it out evenly, right? All right, and now what's our percentage? Our high, it goes from like up as high as 50%, right? So 0, 10, 20, 30, 40, 50. All right, I might not be spaced quite evenly, but it's close enough. Okay. Let's plot our points and figure out what's going on. In 2001, I'm at 1%, so I'm right down here at the bottom. 2004, I'm at 10%. At 2006, I'm at 26%. At 2009, I'm at 47%, okay? So did the curve start low and just slowly rise and kind of keep that, or is it climbing more rapidly? I would definitely say climbing a little more rapidly. So that makes it exponential versus the logarithmic, okay? All right, 2 more I want to do here. This next one, simply just pulling it into your, so you're kind of exposing you to it. Let's leave it at that, exposing you to it, okay? Because I'm just going to tell you right up front, I'm not going to make a test question that comes from this, okay? Just giving us this idea that you can take something written in an exponential form and you can write it with a natural log in it, okay? Why would you do that? Again, that idea of changing the form of things, okay? So it's saying that you can take this and this number out front, this 4, it's kind of like my stretch or shrink, right? It doesn't need to move. But if I have 7.8 to the x power, I can change that to e to the natural log of 7.8 to the x power. And that's all it's doing, is it's expressing this as a base model, basically. So that 4 goes nowhere. I take the 7.8 to the x, and I take it to e to the natural log of 7.8 to the x, okay? So it's taking it, kind of like before, we would have crossed off the e in the natural log, and we would have just made it 7.8x, okay? Which is what we see there. But this is saying, no, we want to rewrite it this way because we can actually do some math with it. What we can do is hit it on our calculator, and we can do natural log of 7.8, and we get like 2.054, it says to 3 decimal places, x, okay? It's a model, we can use it. What are we using it for? Right now, it's out of context. We could go get a story problem for it, right? But it's just giving us this idea that we can do this. I will not have a test question like this, but I want you to just be aware that it's possible to do this. Because once again, when you get to calculus, sometimes it's like, how can you rewrite this in a different format so that you could do something with it? Okay, to be honest, of all the problems we do, I feel that example 8 is the most realistic for our real world, okay? And I will show you something like this on a test. It says, what interest rate to the nearest 1/10 of a percent is required for an investment subject to continuously compound to double in 10 years? Legitimate question. If I want to double my money in 10 years, what kind of fund do I need to put it in, right? What's the interest rate it needs to be? Okay, a couple things here. Continuous compounding, okay? I will give you this equation for the test, but don't forget, this is our PERT equation, right? A equals P to the ERT power, okay? PERT. All right, I want my money to double. So we did this earlier, kind of the flip side with the half-life. They didn't tell me how much money I have. So let's make it up. I have $1 right now. If it doubles, it's going to $2, okay? Remember, whatever numbers you put in here will eventually reduce to the same thing. So it doesn't matter. Just put in values that take your initial and double it for the second, okay? E is E. We don't know the interest rate, and we want to do this in 10 years. Okay, so as always, we need to get our exponential by itself first. Okay, if this number was not 1, we would need to divide by whatever it is. Because my number is 1, I'm good, and I can just leave it there. But I do want to stress, if you had a different number there, make sure you divide by it. Now that my exponential term is by itself, I'm going to take the natural log of both sides. So now I have the natural log of 2 equals, my e and the natural log cancel, 10r. So to get my interest rate, I'm going to divide by 10. And I do the natural log of 2 divided by 10. Special note, that 10 has nothing to do with the natural log, so don't include them together. Simply find the natural log of 2, get that decimal, and divide it by 10, okay? And my rate here needs to be 0.0693, which that's my rate as a decimal. So if I want to find my interest rate, it would be like 6.9%, okay? Otherwise, almost 7% for me to be able to double my money in 10 years. Let me know when you find that account. I want to invest, okay? All right, modeling. It's why we learn things, to be honest. I know we hate story problems. I know we dread them. I know we're like, why? It's because that's where we use this math in real life. Somebody in this group may need this someday. If you're going into banking, if you're going into loans, this last question is a huge one that your customers might ask, okay? Or an investment, something like that, okay? So practice, page 447, I suggest 3 through 54 by 3s, 55 through 58 all. You know what you need to practice and get proficient in it. Not practicing means you will not be proficient, and that next test will be really hard. So please practice.